This talk is the story of my work in Lightrix, a recently new unicorn based in Jerusalem, Israel. Our company does mostly image and video processing apps, mostly to iOS, and I was tasked with converting the rendering engine of our boosted iOS app from iOS to the web, both the backend and frontend, and I wanted to use C++. Now, before I started the process, I was informed that by the manager of the iOS app that the interpolation, some parts of the engine are less than optimal. And so the CTO suggested that instead of using the old object-oriented design that we used for the engine, I'll use a data-oriented design in order to do that. So what were we talking about? This is the story of how I did this conversion. In order to start, let's just talk about what I'm talking about when I'm saying data-oriented design. Usually when we talk about object-oriented design, we're talking about building code as it applies to single object. You have a car with 4 wheels. You might, in practice, use thousands of cars. You might use thousands of the objects, but you write your code referencing a single car. In data-oriented design, that's not what you do. In data-oriented design, you treat your software, the code that you write, as a manipulation of data, as what is the computation that is about to be done. So you don't, if you're going to move thousands of objects, you don't write your code when as if you're only handling a single object. You don't write your objects as if they are individuals, but you're asking what is the total of the transformations I should do, and I designed the code that way. I designed the code in a way which is not necessarily the most readable, but in a way which takes into account what the code will actually become, what instructions the CPU will run, and in a way that, when taking this into account, minimizes the usage of slow, inefficient things, and essentially tries to take into account what will happen in order to run as fast as possible. That means that whenever we try to encapsulate code, encapsulate our logic, we don't go with conceptual things like objects, but with what is in practice going to run, what the actual functions that should be run, what are the actual operations on this data that should be done. And part of that is saying we don't think about the abstraction because there is no one single perfect abstraction to handle these computations. We think of data and handle the data as it needs to be used. This means that your solutions sometimes are per platform, per situation, and not a single object that tries to handle everything that can be done. Now, the specific problem that I'm going to describe today is the problem of video properties interpolation. Now, in order to show you, in order to explain it, first I'll show you what I mean. This is an example of interpolation. You see the text, it's moving, it's changing its color on the screen, and the values that are of the text change between each frame of the video. So what I'm talking about, we have several items being rendered in the video. We have the background image, we have the text. Each one of them is represented by a model. Some models have different properties, such as X or Y coordinates or RGBA color values. At different points in time, they change their value. They interpolate the value. So for every frame, we need to calculate the values required for that frame. Now, when we do that, we say that not all values interpolate at every frame, and not all values that interpolate in the same way. That is to mean that different models interpolate the same values in a different way. And within a single model, different values might interpolate in different ways. So this is a classic case for polymorphism. We have several types of models. We saw text and image. There are a lot more in our real code. Each model has different number of interpolatable properties. Each property might be interpolated in a different way depending on the model. And at compile time, we don't know what models will be run because the user might add more text, more images, etc. So when you say, I don't know what will happen at compile time, this is exactly the case that we want to use polymorphism and have runtime and determine these things into the runtime. Now, I'm going to go now into the code and start explaining how the code looked initially and how and why I change it over several steps. Now, before I do that, just a couple of things to clarify. First of all, the usual caveat, this is presentation code. Assume it was simplified in order to be more readable. I will stop at multiple points during the presentation in order to ask for questions. If you do not understand what the code does or what is the intention behind the code, please ask in the Q&A section and I will try to answer. This is very important because the code builds on itself layer after layer. If you do not understand what it did initially, you will not understand why I changed it later on. And so you will get less out of this talk. So please ask often. Don't wait for me to prompt for questions, but I will do that often. And for those that want, I made a sample of the code in a public repo that can be accessed by anyone. If you want to see the code, see examples of what I'm giving you, benchmark them. And of course, if you think you can do better, PRs are welcome. The link will be available again later on, and also the slides will be available. So you don't need to hurry and copy the link right now. So in a high level, what are we talking about? We are talking about rendering a single frame. And in order to do that, we take two steps. First of all, we interpolate the models in order to create the models. We interpolate source models with the given time in order to create new interpolated models for the current frame, and then we render the models. Now, the second function takes the models as a const vector. It does not modify them. It does not mutate them. And also, we will not go into it. The first function is what we're going to discuss, where we are taking old models, creating new models for the given point in time. Just as a notice, initially, we created new models every time because we like immutable objects. We like to know that if we're changing an object, we will throw it away so it will not affect the run of the program later on. So let's get into the code. When we're talking about a model, first of all, we need to discuss its components. We have an enum determining all the properties across all the models. And we have update operators, which explain how a property is modified when it receives new values. We have various interpolators. Here I just used one that gives us lerping. And we have animations, which determine which property needs to be modified and what is the function that presents a new value. And then a simple function that takes a source value, an update operator, and a new value for the given time and combines them. I think we don't need to go into into how the function is built. It's mostly just a switch case that takes the enum and applies the relevant operation over it, over the two values, sorry. So when we're talking about models, what are we talking about? We have a class, which is an abstract class. It has a single public value, a single public method that takes a property to update and a value at a point in time and updates that value in itself. We have, in order to do that, two protected methods that are virtual and abstract for the base class, which allow us to get both the correct update operator for the given property, for the given model, and a reference to the point in memory that needs to be updated. And also we have a method that allows us to make a copy of the object and a container of all the animations that need to be run over the given model. So how do we interpolate them? Very simply, we have an array of a vector of input models. We have a point in time. We create copies of each model. We modified the values in the copy. We push them into a vector and we return the vector. That way we get copies, which will, any change you will do in them will not affect the source values. We do not modify the state of the source value. So this operation can be done on every frame without worrying that the operation on one frame affects the result of another frame. And this is, I think, nice, simple code. Soon we'll see that it's not the most effective or performant code. Now, this is the base of the code, how it was structured before I started editing it. Are there any questions about it? I'll wait a couple of seconds and answer them if there's anything. Okay, so no questions. So let's talk about what's problematic about this code. The first very simple problem about this is that on every frame, we are creating a lot of new copies. Now, because we're using virtual inheritance and because we don't know the size of each model ahead of time, we need to dynamically allocate the new models. Now, this is simply put a very expensive operation. If we wanted, allocating new memory is expensive. I'll go a bit more into that later on in the talk, but we'd like to avoid it if we could, just not pay the price of so many copies. So let's remove them. We had the make copy method that we used before. How can we replace it? Simply by caching our copies. If we always ensure we have only a single copy and we reuse it by resetting it before we start interpolating its values, then we can be reasonably safe knowing that as long as we have a way of safely resetting it, the fact that we are reusing the copies between frames, and although the copies aren't really immutable, well, we still can assume that one frame does not affect the other. This is less safe than the code we had before, but it removes the first expensive thing we have to do. So the first lesson, let's avoid dynamic allocation when possible. It's true that immutability gives us a lot of safety, but when immutability comes with a requirement of dynamic allocation, we might need to balance it with performance. Now, before I go further on, let's expand a bit on this because I'm not sure how many of you are well-versed in virtual inheritance. Now, the problem we have is that different models have different number of properties. Essentially, each model has a different size and memory. We have to access these models via a pointer to them, because we don't know how much memory they'll take if we put them on the stack. We must put them on the heap. And creating a new object on the heap means it is put somewhere in memory. We're not sure where. Usually it is nearby other objects, but not always. Now, the same is true not only of the object, but also of their methods, their virtual methods. The methods are saved in a virtual table. The virtual table is saved somewhere in memory for each type of model we use. And so we have a lot of lookups in memory, both to find where did we allocate our objects, and also where are the functions, the methods of the objects when we try to run them. So let's try to demonstrate it with this diagram of the memory. We have our input, a vector of models. We iterate over it. We start going to the first model. We find the first model's virtual table. It is of one type, that's its virtual table. We allocate a new copy of the model somewhere else in memory. Then we go into the internal vector of animations in that model, and we start iterating over the animations of the model. Each animation that we use changes a value inside the copy, so we're jumping back and forth between the location of the copy in memory and the location of the animations in memory. And then once we're done animating all the values in the first model, well, we start animating the next model. We find the next model's virtual table. We create the next model's copy, again, somewhere else in memory. We find the next model's animation vector somewhere else in memory, and we start animating these values too. Now, this is a bit of a caricature. Usually, memory allocation will be better spaced and will attempt to put things together. But still, this is the problem. Things are located in different places in memory, and memory access is slow. It is so slow that it is considered slower than computing multiple things and than making multiple calculations. But our CPU has a memory cache. I will not go in depth into the way the cache is structured, but simply put, if you access memory that is near recently accessed memory, you get a cache hit, and that access is much faster. If you're accessing memory which is far away from recently accessed memory, it's slow. It's called a cache miss. So we would like our memory to be structured in a way which is very local, in which the things we access one after the other are placed in memory one near the other. So in order to do that, first of all, we might consider other forms of inheritance, because as I said, the problem with virtual inheritance is that we have to use the heap. We have to trust the allocator to put things in unknown places in the memory. If we use, for example, stud variant, then everything might be on the stack. We will not be using virtual tables. And so we will have better locality. We will not be using virtual tables or pointers. Now, there are multiple problems with variants. They're verbose. Their stud visit is less than optional. We can do things better. We could create an allocator or use a custom allocator which matches our use case, and so allocates things exactly as we want them to be. But the problem with that again, custom allocators are verbose, they're complex, and if the custom allocator you use is not really tailored to the specific layout of the problem that you expect, then the benefit from using them might not be that great. The third solution is just to build a data model that matches the way you access the information in memory, and essentially build it ahead of time so everything will be laid out where you expect it. So in order to give you a good example of that, I'd like to go into my favorite edition of C++20, which is StdSpan. StdSpan essentially is just a way of taking contiguous memory, a contiguous memory collection, such as a vector, and choosing a part of it, taking a subsequence of the collection. If you're using C++20, you have it in the standard. If you're not using C++20, you can get the GSL library and use it right now. And it is, in the way I'm using it, is a way to logically separate a large array into smaller arrays. I'll show you in a minute how I'm doing it, but just as an example, this is as simple a way of representing a span. It is a pointer to a beginning of contiguous memory and a length determining how long is this current sequence. It's small, it's easy to move around, it's fast to move around, and it allows us to use it using iterators, etc. And so it gives us a similar API to using other collections. So where were our problematic vectors that we're going to use with the spans? We'll begin with the animations vector. If you remember, each model had its own animation vector. We can move all of our animations into a single vector that is separate from all the models, and have each model just contain a span into the shared animation vector. This means that all the animations will be laid out one after the other. And once we iterate over all the animations of one model, we'll continue iterating into the animations of the next model without moving around in memory. So it's very simple to do. Just take the vector of animations and replace it with a span of animations. And when you create the different models, just create a single vector of animations with all the animations in each model. This is not a significant change in code, but it might give you a significant change in memory, in performance. But that's not all. See, we don't need to actually have, look at everything as a vector. We don't need to have the interpolatable properties inside each model. It's easiest to us to think of a model when we put the properties inside the object. That's the object-oriented way of encapsulating the data of the object inside the object. But it doesn't have to be so. We can have a single vector of properties for all the properties of all the models. And in each model, instead of having the properties, just have a span that points to the properties vector. And we use two property vectors. The first one is the source properties, from which we take the value that we will interpolate. And the second one is the result properties vector, into which we write the results of the interpolation process. So again, the change to the model is not very significant. We add a span of the float interpolation properties into the base class. And when we're looking at the inheriting classes, instead of having the properties built in, we just have the span, and we can add getters and setters if we want, that just know ahead of time to which index in the model each property is mapped to. If we want, we can have even a spans with set size. Instead of having a generally sized span in the base model, we can have spans with set sizes inside each model. So how does this look in memory? Again, we go over the input, we iterate, go over the first model, find the first virtual table, create the first copy. But then when we start iterating over the animations, we go somewhere else. We have an animation, properties, and property copies vectors. We modify them, iterate over all the animations. Then when we go to the next model, we start returning to memory that we've accessed before. And again, the heavy operation is done here between these three vectors. Most of the work is done in this location in memory. And so we consistently return to the same places in memory, thus increasing the chance for a cache hit, for not for keeping our memory that we're doing the most of our work on in the cache. So what's the lesson we learn here? We should strive to increase memory locality on memory that we access often. It is much better to use a single vector and multiple spans than using multiple vectors. And if you want to take it further, read up on structs of arrays or entity component systems, which are essentially a way of taking apart objects into several vectors, each one containing the information needed for certain transformations, so that each object only has indices into its components instead of actually containing its components. Are there any questions about this? Okay. First question, is there not a problem with spans being invalidated when the vector resizes? That's a very good question, and the answer is yes. As far as I know, there will be problems, but this shouldn't happen. First, you create your vectors, whether you pre-allocate them or iterate over all the models and find out what sizes you need. And then after you've finished creating your vectors with their final size, then you create the spans. If you're trying to create the spans while pushing things into the vectors, yes, the vectors will resize and your spans might be invalidated. Okay, our second question is, how do spans prevent cache misses better than vectors? So a single span does not prevent a cache miss better than a single vector. But each vector is dynamically allocated. So you will have one vector with its memory allocated in one point in memory, and another vector with its memory allocated in another point in memory. So once you finish iterating over the first vector, I'll just go back in the slides and demonstrate it. Once you finish iterating over the first vector, you need to find the location in memory of the second vector and start iterating over it. So you almost certainly promise yourself to have a cache miss on the second, once you move to the second vector, right? So you see here that we have the first animation vector. Once we finish iterating over it, we go to the second animation vector. Once you finish iterating over the properties of the first object and the first copy, you go to the second copy. And again, promise yourself a cache miss. If, on the other hand, you have a single vector and multiple spans, and in case I didn't mention it, build the spans by the order in which they will be iterated upon. Then once you finish iterating over the values in the first span, your next operation will be in the second span, which begins just later on in memory. It's the next step in memory, and so it's much likelier to have a cache hit in such a case. And I'm sorry, I don't see how I can remove the Q&A, so sorry about keeping the questions on. Are there any more questions? Thank you. Okay, so the next thing to tackle is instructions. Instructions, the actual operations that the code tells the CPU to run. Instructions are saved in memory. And so whenever the CPU tries to understand what is the next operation it needs to do, it accesses memory. Instruction fetching is memory access. Now, instructions are everything the CPU needs to do. And sometimes an instruction is go to a virtual table and find out what's the next function that needs to be run. So there is a step of indirection. You need to make 2 steps in order to get the next instruction. And because the virtual table is not necessarily located near the current instruction, the command go to a virtual table again reduces locality. The more virtual tables you have, the more model types, that you access in your succession means that you're jumping around different memory tables. You're having more memory accesses into different locations in memory, which means more cache misses. Also, you reduce the ability of the CPU to predict what the next operation will be. And again, that slows down the operation. So I'm not going to go much into depth in that, but essentially read up on branch prediction. It's what the CPU does when it tries to expect what's the next computation it will need to do. Now, it's not only virtual tables, it's also large loops. If your loop does a lot of things, then once you iterate over all the instructions in the loop, reach the final instruction, and which is essentially jump back to the beginning. If there are a lot of instructions there, then jump back to the beginning will be to a faraway point in memory, and that will be another cache miss. So also, just the same way that virtual tables reduce locality, large loops that do a lot reduce locality. And our loops had, well, they're large and they had a lot of virtual calls in them. Let's look at them. So we had the call to make copy, which was virtual, whether it is the initial implementation or the second one. But that's not inside the inner loop. In the inner loop, update value had 2 virtual calls that were done inside, both to find out how do we animate the current property, and also in order to get the location and memory of the property that needs to be animated. Both of these are specific to the current model. And so they were done using virtual calls. We would like to separate them out. Like to take this loop. This is the hot loop. This is the place where the values actually interpolate, right? And we would like to move it outside, make it a tighter loop that will not access virtual tables. How do we do that? By the magic of pre-processing. Ahead of time, since we know before we start going over the video, we have all the models, we can predict what animations, not predict, we can read the animations, read the models, and construct a struct that will tell us exactly what needs to be done for each property. So for each property, we have an initial value, the initial value of the property in the model. We have all the animations that will run over this property. Again, this is a span into the shared vector of animations. And notice that here we don't need the animation, the animation struct, which contained the property to animate. We just need the interpolator function, functor, in order to have the current interpolation, and the update operator, because the update operator is consistent for a given property and a given model. So we create ahead of time for all the properties in all the models a vector of these input values, which tell us how to animate each value for each frame. And then interpolating values is much faster. We have our vector of inputs, and we have the target vector the floating points, which is of the properties into which we will write the new values. And now we just iterate over the input values. We get the initial value, and then we iterate again over the animations. We receive the value from the given animation for the given time, and we update the value. And then we write the result into the target vector. And here, we don't know what's the model, and we don't care what's the model in which the property was given. We also don't know what's the property that we're interpolating. The only thing we care about is the values and how do we combine the values. Values, animations, and how to apply them. We do not have the higher level abstraction because we do not care about the higher level of abstraction for this internal function. This is what I talked about earlier about considering what is the actual data manipulated. Ahead of time, I told you this is about interpolating values in models. Now, the manipulation we do is interpolating values. We do not care whether these values are in models or aren't in models. We find the essence of what we're doing. And once we do that, we don't even need copies. So what have we improved? Here, we removed the repeated virtual calls from being run on each frame to being run once during pre-processing. This means that as long as we have more than a single frame in a video, we have significantly improved performance. We removed the need for dynamically allocated copies, whether it is a single copy or a single copy for each frame. We don't need them. Each model can just have a span into the target properties, and that's all they need. They don't need to be copied anymore because we don't have the idea of source model and copy model that can be passed onwards. And we separated the concept of model creation from interpolation. We separated actually the whole model handling from the process of interpolation because, as I said, during interpolation, we don't care about the object that contains the information. We only care about the information which is being transformed. And as a result, this gave us a tighter loop. We don't need to go and check each model before we start interpolating the values of the model. We don't need to leave our internal loop in order to check some wider scope. We have a single loop iterating over all the values that need to be interpolated without checking additional information. So what's the lesson? When you have hot loops, loops that must be performant, are repeated often, have to be finished quickly in order to not give the user too much delay, you don't want to have virtual calls in them. You can move virtual calls outside of these hot loops by pre-processing and creating information that tells you what needs to be done here. When we have tighter loops, we have instructions that stay in hot memory. Less instructions increase the chance that our instructions will stay in memory and we will not have cache misses, and the CPU will be better able to predict what's the next thing that needs to happen. Any questions about this? Okay, can spans be grouped separately? Would every span I defined be put into one big group of adjacent spans? I am not sure what do you mean by this. One big group of adjacent. I'm not sure what's the scenario that you would need to use it, but if you need to have subgroups amongst your models, then sure, you can have a subgroup of each span. But again, I would ask, do you really need these subgroups? Or if you're just iterating over the information in these spans, does this operation care about whether the outer abstraction, the models, are separated in one way or the other? So I'm not sure what scenario does this mean to serve. I would hazard say, yes, you can do that, but maybe there's a way to not do that and not jump around in memory. Second question, what is the HOV overhead and the bookkeeping of the system responsible for handing out the spans? Okay, so in our case, there wasn't a situation where models were being destroyed during the runtime, or some, to be exact, where some of the models were being destroyed. When the user changed the video in real time, then we would just remove all the models and recreate everything from scratch. If you wanted to reduce your safety and increase your efficiency, yes, you'll need to start doing things like removing spans from the middle and moving the spans after them back around. And essentially, you'll be doing all the things that a memory allocator should be doing. I would hazard, if you're doing that, you're going into very complex territory. And maybe in such a case, you might want to use the memory allocated more and not try to create your own data layout. We, as I said, in order to prevent these problems, we just let, whenever the user changed anything, we destroyed everything and recreating it, because creating the models once is expensive, but it's not that expensive when amortized over all the frames when the frames are being played. So again, this is, as always, you need to balance your safety, the readability and maintainability of the code versus the performance improvement you'll get out of it. In our case, we thought it would be much safer and simpler to destroy everything and create everything from scratch on every change. On slide 30, yes, let's go back to slide 30. Yes. On slide 30, how can we use a span there? Do we know that all these animations are going to be continuous in the original vector? Yes, we can know that because we are the one that are building the original vector. If we are building the original vector in a way that assures us that all the animations of a single property will be one after the other, we can assure that. And this might require sorting, it's true, but which is less than linear, it's less than optimal maybe, but it's only being done once. And we're willing to pay a price once during pre-processing in order to not pay the price later on every frame. So yes, we can know that because we ensure that. And we can make the extra effort because it's making the extra effort once in order to achieve better performance over hundreds or thousands of repeating frames later. Did I quantitatively measure my gain in performance, especially regarding the instruction cache? That's a very good question. And the answer is yes, I did measure my gain. And in the GitHub repo, you have a very basic benchmark, but you can measure the gain there too. And you're, as I said, more than welcome to check other options and see what the gains are there. Specifically regarding the instruction cache, I did not go into that kind of resolution, no. And if I understand the thought behind the question, I do agree that essentially when you're going into the optimization of asking how much memory do my actual instructions take, then you're going into the very extreme points of optimization. When you're asking how can I optimize every nanosecond away. I can say unequivocally that removing virtual calls was a noticeable performance gain. And I can say that the changes to the tighter loop were a noticeable performance gain, but it might have been a performance gain not because of the instruction cache, but simply because I removed the access to the models in between in there. So I can't say exactly what was the source of the what was the source of the gain. Sadly, as I mentioned before, most of the work is done in the front end in a browser in WebAssembly, and WebAssembly still doesn't have great tooling for this kind of question. So you need to make some assumptions and hope for the best. Okay, if there are no more questions, I would like to go into the places where I failed, because it's very easy to talk abstractly about what did you do and how did it increase performance. But sometimes, even if you take all of the best thought, you need to benchmark and find out that not everything that should have maybe you thought would be an optimization is an actual optimization. So let's look at the first thing that I tried. The first thing that I tried was saying, okay, maybe some models share the same interpolators, have the same interpolation function. I can have multiple models access the same interpolators instead of having a span of interpolators for each model, just have a span of indices to the interpolators, compute the interpolation value for each interpolator ahead of time, and then later on, in the second part of the loop, I will just access these results. And if I have multiple models or multiple properties which are animated in the same way, I will save the cost of computing the same thing multiple times. That should be quicker. So what do? I pre-compute the values at the beginning of the frame, and then I fetch the result of the computation instead of computing it for each animation. Why was this slower? Well, first of all, if you've listened to me before, you might have noticed that I explicitly said it. Memory access can easily be more expensive than computing things. So when you're jumping between two vectors, between the vector of the properties and of the results and the vector of the properties, you incur another access into somewhere else in memory. This can easily be more expensive. And more than that, my assumption that a lot of models share the same animations was just plain true. Very few models shared the same animations, and the cost of accessing, of both still doing the animation and then adding a jump in memory in order to get the result instead of having it directly available here at the first line of the internal loop, well, that was just too expensive, and that became slow. Let's go over that again in case you've missed. The interpolation was calculated separately of the update to the properties, which I thought is an even tighter loop, should be even faster. The interpolated results were saved to a vector, were retrieved to a vector, and that wasn't faster because I added to the process another memory access on every property. Another optimization which I considered was simply saying, listen, I'm iterating over every property and not every property animates. In fact, the vast majority of properties don't animate in a given video. Most things stay in place. Most colors don't change. The intensity of most effects does not change. So I don't need to iterate over every property. I just need to iterate over every animation. And then I construct a different struct of animation, which tells me, again, how to animate the value, but also where is the property that needs to be animated instead of the old structure, in which the property had a pointer to where the animation of the property is. And now I have a tight loop in which I compute the value from every animation. I find the value, I compute the animation, And then I combine the values and write them back into memory. And this should be, at least iterations-wise, this should be significantly slimmer because I have less animations than models. But it was slower. It was measurably, by a naked eye, slower. Why is that? The reason is very simple. Because every time I animated a property, I read from memory and wrote to memory ahead of time, and the compiler could not optimize over it. That was a case where we just went into a decompiler, tried to understand what is happening, and saw that the compiler could not optimize this memory access away. Shouldn't be a new lesson. Let the compiler do its optimization. If you're reading and writing from memory in such a way, it might slow down. It probably will. So we thought, okay, let's tell the compiler what we are trying to do. So instead of reading from memory, we will just, ahead of time, check whether multiple animations are animating the same property. We will read the value from that property once. Then internally, we'll iterate over all the animations that animate this property. We will accumulate the value from all the animations, and only at the end we will go and write these things into consistent into memory and write the result back into memory. This should teach the compiler what do we intend to do. Reduce the number of iterations because, again, we have less animations than the property, and should be faster. And was it faster? It was roughly as fast as the final implementation that I've shown you before. Why was it not faster? Well, I cannot tell you. I don't understand. And I think that's the final lesson. Everything I told you so far is only true once you benchmark it. It starts with the question, is your code slow? Does it need to be more performant? Don't guess that. Don't say this code looks slow to me. Benchmark it. Is it an actual problem? Is the problem where do you think it is? Only then come and optimize it. And none of what I said is an actual optimization until you benchmark it, you benchmark the change, and can measurably and reliably say, yes, this was an improvement. I think that a lot of people in a lot of data-oriented talks say unequivocally, data-oriented design is better than object-oriented design. And I think that, yes, performance-wise, it is better. But you don't need to go and overhaul your code. You don't need to write in a paradigm which isn't intuitive, accessible, or readable to you or to the rest of your team if you don't have to. Nothing is better until you've measured that it is better by the parameters that you care about. Where you care about performance, find what is slow, understand why it is slow, and improve that. Are there any questions? Okay, was implementation 2 slower than expected because the output locality matters as much as input locality? That's a good question. It might be, I don't think, because the value should be kept in a register. And both in the second implementation and the original final implementation, we still have a separate input and output. So value should be kept by the CPU in a register, should be, at the hottest of hot memory. And nothing else here is more memory reliant or in a more fragmented memory than the former implementation. So I'm going to go with maybe, but I don't think so. Second question. I'm a bit concerned that you're leaking lots of implementation details into the API of your code. Is the result still maintainable? How do you deal with keeping the rest of your application data sane? That's a very good question. And in case it wasn't clear before, everything that I told you so far has its cost. There is a cost to being, there is a cost and there is a balance to be struck between readability, maintainability, and the ability of people to understand what your code does. In our case, this wasn't a consideration because we still had the models. As I've shown you before, we had the getters to the properties that allows us to abstract away the fact that the properties are not inside the models, but rather kept in a separate vector. So all the API afterwards inside render models did not need to take into account the logic inside the interpolation process. So this did not cost us in maintainability. The only changes were into the interpolating a value function and to the way that we initially created the models. And these two were very localized changes and so easy to maintain. If you're finding out that the change requires a change in a significant change in API, yes, it's perfectly legitimate to say the solution is faster but less maintainable. Let's find a middle ground that is faster but still maintainable enough for our requirements. Another question. On a scenario where not all objects are known from start and some are created and or destroyed during a rendering loop, how would that be handled? I would say it's similar to the question asked before, and I would say again, try to avoid that. The more things, well, this isn't new, right? The more things a code can do, the more complex the situation, the less strong you have, the less stronger the assurances of what is actually happening. If you need to have values disappear from the middle of a vector, how do you handle that? It's not easy. It might be better, for example, to have another property, another vector of, well, vector of bools, if you're feeling adventurous, just saying this object is used or not. And before you actually go around rendering an object, check if it's used or not. That's what we do. One of the properties we interpolate is called opacity. It is how clear the object is. Objects and models with zero opacity are skipped during the rendering loop. They're not destroyed. They're not removed from memory. So our memory structure is still coherent, but they just aren't rendered. So I would say try to avoid creating or destroying things in the during a rendering loop. Don't do dynamic allocations inside the thing that repeats over and over again. Don't free up memory and try to handle having, gaps in your memory during the intensive loop. Try to build everything up once during pre-processing, including making room for, if you can, all the models that possibly will be created, and just have properties that tell you what should be used, where, and when. I think it would be safer, it would be easier, and I can't account for your scenario, but I think it will also be more performant, again, because you will not be doing all these memory allocations and frees during your most intensive parts. But if you have to do that, then yes, you need to have some way to account for things. You need to be able to move spans around, and that will be both complex and also probably less performant. I believe that is all. Thank you very much for participating in the lecture. And once again, thank you very, very much to the organization for this lovely conference. Ta.